the benefits of science will be even more spectacular than we can ever imagine. I wanted to do something that is of long-range benefit to humankind. Practically everything we touch in our daily lives has been developed and improved through basic research. Science is taking us on an ever-accelerating journey into the future.
Please join me in welcoming to the stage 2026 ACS President, Rigoberto Hernandez.
ACS 150, chemistry is everything.
Well, I know I'm inspired. Good evening and welcome everyone. I am Rigoberto Hernandez, 2026 President of the American Chemical Society. And it is my sincere pleasure to welcome you to the ACS Spring 2026 Lecture Series sponsored by the Kavli Foundation. Reflecting the mission of the ACS as well as that of the Kavli Foundation, this lecture series promotes groundbreaking discovery and public understanding of many of the world's challenges and how chemistry provides solutions. The ACS is grateful to the Kavli Foundation for enabling us to highlight the achievements of outstanding researchers in the chemical sciences. The Emerging Leader series shines the spotlight on scientists younger than 40 years old who have made exceptional contributions to scientific or engineering research. Tonight, I am pleased to introduce Professor Rachel Carter of the University of Kansas. Dr. Carter, yes. Dr. Carter just joined the University of Kansas as an associate professor in January of 2026 in the Department of Mechanical Engineering, where increasing innovation in chemistry is mushrooming. Prior to that, she conducted materials research at the U.S. Naval Research Laboratory. At NRL, Dr. Carter focused on safer and more effective uses of conventional lithium-ion batteries, as well as batteries made from more abundant materials, which many of you find today in your cell phones. Dr. Carter received her PhD in mechanical engineering from Vanderbilt University in 2017. Her dissertation research focused on material and processing challenges for alkali sulfur batteries. In just her 10+ years as an energy storage researcher, she has published 67 peer-reviewed articles and obtained 5 patents. In 2019, Dr. Carter was recognized by Nature as a top 5 emerging materials scientist. She was recognized in 2024 as one of CNEN's talented 12. And in January of 2025, Dr. Carter received the highest honor given by the U.S. federal government for early career scientists, the Presidential Early Career Award for Scientists and Engineers, known as the PCASE. It's my pleasure. Please welcome to the stage Professor Rachel Carter.
ACS 150, chemistry is everything. From atoms small to the lives we
Congratulations
shape it.
again.
Every bond, every reaction, science moving us into action.
Thank you so much, and what an honor to be here. And I'm really excited to talk to you guys a little bit about my research. So the topic today is understanding interactions between temperature and battery phenomenon. And as we just learned, I'm now at the University of Kansas, but much of the work that you're going to see has been done at the Naval Research Lab. And I want to well acknowledge the number of collaborators that I've worked with that have made this work possible, and I hope I acknowledge them throughout the presentation. So first, why batteries? So when I decided to do graduate research, I was really looking at different topics to try to work on and considering what can make a difference in the world. And all of the technology that we develop and uses a battery. So all of you likely have a battery on your person. More and more we're using even more batteries. We're projected to continue to use more and more batteries as we try to transition to more cleaner energy sources. The primary goal right now is to electrify transportation. I've put some images here of different batteries that you might think of when you think of batteries, where you might be thinking about their use. And the reason that I'm going to talk about temperature today is that temperature is a key element in many of the governing equations. And more we're using batteries in really extreme environments. So drones are a great example. We just got done with the Winter Olympics. Many of you probably saw those drones chasing down the athletes. They're powered by batteries that perform in a very limited capacity and low temperature. And so we're going to talk a little bit about that throughout the presentation. Okay, so just to briefly discuss the simple mechanisms of batteries for those of you who are working in other different areas, it was a massive advancement for the lithium-ion battery to be produced because it really enabled the use of portable electronics and this electrification of transportation that I was speaking of. And the reason why it was so revolutionary was this layered structure that I'm presenting. So we have sort of 3 main components: an anode, a cathode, and an electrolyte. Both the anode and cathode in a lithium-ion battery have a layered structure that has specific locations to host lithium-ion batteries. And this provides many cycles. So we still often complain about our batteries dying over a year's timeline. But before the lithium-ion battery, we were really using chemistries that died much more rapidly. And so the way this works is we transfer the ions from the lower energy state in the cathode. As we begin charging, they move in an orderly fashion into a location to be stored in the anode until they fully fill up their spaces in the anode. So again, this layered structure is what gives us those mini cycles that facilitate their use in a wide range of applications. But because they have these locations that they need to move to very precisely, if we move too quickly or too slowly, we can have the ions order themselves in an improper fashion within the anode, or accumulate and deposit as metal on what we call the solid electrolyte interface, or the SEI, this purple layer that I've drawn. And so when we have these sort of undesirable mechanisms of charging, this is often blamed for these catastrophic failure modes, which are also hallmarked by the lithium-ion battery chemistry. And so although they're massively enabling technology, this one failure mode is very concerning and gains a lot of attention. So the limited rate capability and also their sort of material supply chains are primary concerns at this time. So I mentioned that we continue to use more and more batteries, and batteries are surprisingly safe. So the events that we observe are 1 in about 5 million. But now that we're aggregating many, many batteries, those failure modes are happening more and more because we actually have those quantities of batteries where the risk is more probable. And so this is just a representation from literature of the number of safety events which are occurring, and you can see a rapid increase from approaching 0 in the 2010s to now 120 vehicle events per year. Okay, so at the Naval Research Lab, this work was funded by the Naval Research, Office of Naval Research. We were particularly interested in low temperature operation. So we're looking at environments where we're either under the sea or in the air. And so low temperature is often considered to be a case where that plating phenomenon is most likely to occur. So the Navy is a great place to do research that is pushing the boundaries of battery operation. And these boundaries are things that consumers are now doing as well. So we're using batteries, up in Alaska and using drones in consumer applications. So this was a really nice use of government funds to understand something that's important for all people. And so we basically just compared the battery cycling of a battery at 20 degrees Celsius compared to 0 degrees. The 20 degrees cell has minimal capacity loss over 100 cycles, where we can see the one cycled at low temperature starts to lose capacity within about 70 cycles. And so here I collaborated with a summer faculty from UC Irvine, Irina Zenyek, and she taught me how to do micro CT analysis. And what we were able to do is get a look inside the can of the battery and see this collapse phenomenon that had occurred into the core of the battery. So what you're looking at in these images is CT renderings that are going down the core of the battery. So the top image is what a battery looks like in its pristine state. And the bottom one is after cycling at low temperature. So we can see this mechanical collapse that has occurred due to chemical changes inside the battery. And so we were kind of inspired to understand the trajectory of this mechanical phenomenon within the battery. And here I collaborated with Todd Kingston, who was a postdoc at the Naval Research Lab at the time. He's now a professor at Iowa State. He's a thermal expert. And so he helped us understand that if we were to move a battery from a warmer temperature to a cold temperature, for example, driving your car out of the garage or something like that, the temperature of the battery is only changing within its very first charge, very first cycle. And so we did this process and compared this transient charge to a equilibrium low temperature charge, and we saw a dramatic difference in the evolution of the failure within the battery. So the equilibrium condition experienced core collapse prior to the observation of lithium plating, where the opposite was the case in the transient charging. We observed plating, which then proceeded into that mechanical collapse. And so what was also surprising about this transient condition is that over half of the ions deposited as metal and did not intercalate into the anode. That's a very large proportion compared to what we conventionally see with metallic lithium plating. And so both of these cells had similar end-of-life conditions. When we looked at their interior, we see that mechanical collapse, but they have a different history. And so we were wondering how this thermal history would impact their safety. And so we were looking at ways to assess safety. And so what we want to do is study this catastrophic failure mode that you guys may have seen in news reports or other outlets. And so we used a technique called accelerating rate calorimetry. Basically what this does is approximates adiabicity to mimic this cascade of heat releasing reactions, which you're seeing on the left, and does this at a very precise temperature so that we can observe where that onset occurs and compare it for different chemistries and other factors of the battery. And so what we do is we heat the battery in small increments. We wait, which is what this sort of plateau region is. So we wait for the battery to equilibrate to that temperature, and then we seek the temperature of the battery to see if it is heating faster than its environment. And we set sort of a threshold to look that we say the battery is now self-heating and experiencing this catastrophic series of reactions. And we allow the battery to continue into this event and probe its temperature and reactions. And what we typically observe is the event, which is the release of pressure from the core of the battery, and then this rapid thermal runaway. And so what you're seeing on the top right is how we typically compare these types of behaviors. And so what is plotted is lithium-ion batteries with different cathodes. And the final reaction when a thermal runaway is the combustion of the cathode. And so by changing that cathode, we can get a difference in the peak temperature and peak temperature rate, which have a dramatic influence on the safety that's observed. And so I was showing you guys these two different cells which have similar electrochemical energy remaining in them, but they have very different thermal histories. They've experienced a different number of cycles, they're exposed to different temperatures, and when we assess their safety, we see a dramatic difference. The cell that was exposed to this transient charge has a catastrophic can opening. So it has this really dramatic failure mode where the cell that was cycled at equilibrium low temperature, we have this expansion of the can and some material escaping. But these cans are really designed to withstand the failure mode. So the cell that was cycled at ambient condition looks like nothing has really happened to it. So we can imagine that these actual manifestations of the failure modes can influence the impact on the local assets, whether they are human or in value. And so this really revealed to us the importance of temporal variation in temperature on battery performance. And so because of this inspiration, we transitioned to do more fundamental research. So this is an example of applied research inspiring us to understand the chemical underlying phenomenon which govern these processes. And so what we looked to do is understand these temperature variations and how they lead to these safety concerns in commercial cells. So I was kind of showing you guys that we kept the cells at one specific temperature for cycling. This is what several different groups are doing across literature. But as we know, real worlds are not isothermal. So we have changes in season. We even have temperature swings in the course of a day. So a recent work from the Waldman group looked at changing that isothermal condition over the course of cycling. But we're also looking at how to look at these things that mimic more practical environments and how the temperature environments evolve. And so in our more fundamental experiment, we were inspired by the observation of more conventional gradients in metallurgy. So I showed you this example where we transferred the commercial cell from a warm temperature to a cold temperature. That may manifest as this evolution of temperature within the core of the battery, where if we unwrap the electrode, it's experiencing colder temperatures at one end compared to the other. This sort of difference in metallurgy is how we observe dendrites. And dendrites are the term that we use for lithium morphologies within batteries, although they are quite different from those observed in metallurgy. So we had this sort of hypothesis. Since in metallurgy, if we're applying a hot melt to a cold mold, and that produces this undercooling effect, which rapidly produces jagged dendritic structures, could we have a similar phenomenon within batteries, where when we are transporting ions from a hot source to a cold source, well, we have this rapid growth of metallic structures which can short the battery internally. And so to test this phenomenon, I collaborated with Corey Love at the Naval Research Lab. He was my postdoc advisor and longtime colleague. He had developed this optical cell where we can study these phenomenon. And so what we simply did was we applied a condition where we could over-lithiate the graphite. So we have a large lithium source and the graphite target. And something very interesting about the lithiation of graphite is it's a colorimetric reaction. So we can actually see the graphite changing from this dark gray color to a golden color that tells us lithium is filling the layers. And so we see this propagation of the lithium reaction front, and then we also begin to observe some bright white metallic deposits along with the electrode cracking. And those bright white deposits are evidence of metallic lithium plating. So in this configuration, we can apply heat to the lithium source, and that allows us to test out this hypothesis that by heating the source and cooling the target, we would have more evidence of metallic plating. And what you now see is that instantaneously within the observation of the golden color change indicating lithiation of the graphite, we also see that white lithium deposit. And we do not see that propagation of the lithiation reaction down the carbon electrode. So there's much more propensity for lithium plating to occur when we have this thermal gradient. And what was also interesting to us when we zoom out from the frame that we were observing, we can see different lithium metal morphologies as the lithium was growing from the negative electrode to the positive electrode. And this was reminding us of the observations that Dr. Love had made prior to my joining of the Naval Research Lab. And that's that the temperature at which the lithium is plated has a strong control on the morphology of that lithium that is plated. And that morphology influences the safety behavior because of the severity of the shorting event. And so based on these observations, we were thinking about practical designs. I'm actually going to, yes. So we were thinking about practical designs and how thermal gradients may evolve in them. So I showed you in the very beginning that we have these anodes and cathodes and electrolytes. There's also other components called current collectors. And what's interesting about all these different components is they have different thermal conductivities and other thermal properties. And so these ranging temperature properties allow thermal gradients to evolve naturally within batteries, which means that although we can apply these thermal gradients to study them experimentally, they're also evolving in conventional devices. And so a few studies have indicated that by also applying cooling, we're dramatically increasing this effect. So we apply cooling to batteries to keep them from going into these catastrophic heating events. But when we apply heat, we're also adding thermal gradients. So this is a reason that we need to understand the interaction between the thermal management of the battery and its chemical and electrochemical phenomenon. And so this study at the cell level is indicating a similar phenomenon where we're applying cooling and we observe things like metallic plating on one end of the battery as a result of the cooling geometry. So with this in mind, we did some testing on button cells. So these are the type of cells you might have in your watch or your bathroom scale, things like that. And what we did is we tested 4 different thermal environments, an ambient condition, and then a warm and a cold condition. And the warm and cold were at would create an average of that ambient condition. And then we applied the warm and cold to either end of a coin cell battery and produced the cycling. When we heated the batteries, we see that we get a little bit of enhanced performance. So we're just increasing the kinetics and the overall efficiency of the reactions. And we cool them down, we have higher resistance in the cell, and the converse effect, where we shorten the cycles where we're charging the battery to high voltage and discharging it to lower voltage. But we saw something very interesting when we applied the thermal gradient. The actual performance looked very similar to the average condition for the first few cycles. And then we started to observe this jagged charging phenomenon, which we were observing repeatedly between the 7th and 9th cycle. And we diagnosed this phenomenon to be the evidence of metallic lithium plating creating micro shorts within the battery. And we could observe this plating on the surface when we did post-mortem analysis of the battery, basically opening the cells up and looking at their surfaces. So I worked again with Todd Kingston, who is a thermal scientist, and he was able to help us understand what we were actually applying to the battery's surfaces. So there was actually a large amount of thermal resistance in this configuration as a result of the wave spring and sort of pressure applied to the battery. And so we were surprised to learn that we were actually only applying about 2 degrees difference from the current collector of the positive electrode to the negative electrode. So although we were applying a pretty large temperature difference to the outside of the cell, the electrodes were very close in temperature and still resulting in these large, this dramatic failure mode within a very short number of cycles. And so if we consider this sort of phenomenon within a pouch cell, which might be in your laptop battery, we could kind of see how these layers form and that we actually have alternating thermal gradients if one side is hot and one side is cold. And that is because we coat the electrodes on both sides of the current collector. So near the top of the battery where I have some labels there, one pair of electrodes will experience what we call a negative thermal gradient, meaning the anode is colder than the cathode, and the adjacent cell will experience the opposite. The cathode is hotter than the anode. And so we decided to study this phenomenon of the directionality of thermal gradients. And so again, I have sort of the baseline ambient condition, and then what we call a positive thermal gradient. The negative electrode is warmer than the positive, and the opposite, the positive electrode is warmer than the negative. And again, in the negative thermal gradient, the green data here, we see that jagged charging phenomenon indicative of lithium plating. But in the purple one, we see capacity loss, so the cycles are becoming shorter, but we don't see that jagged charging. And so we wanted to diagnose what was actually happening differently in these two different environments. And so we observed the lithium plating, as I mentioned. So we collaborated with Matthew Dubray at HNEI, Hawaii's Natural Energy Institute. And this gentleman does some really unique degradation analysis using derivatives. So he takes the derivative of the voltage profile, and we can diagnose how the reactions within the battery are changing over the cycling. And so these peaks are indicative of specific changes in the battery when we have the ions moving from one side to the other. And why this was really valuable to us is, and he has this tool that is very user-friendly, and you can simulate different degradation modes for your battery, and I highly recommend you check it out if you're interested in battery research. And so what we were able to do is mimic or simulate a degradation that was positive electrodes or cathode-centric compared to that of an anode-centric degradation. So on the top, you're seeing failure modes called loss of lithium inventory on the left in the cyan color, and then loss of active material specific to the positive or negative electrode. And then in the row below that, a combination of loss of lithium inventory and active material at either the positive or negative electrode. And we were able to see that we can simulate the degradation mode, which looks much like the degradation modes that we observed, and we can track how these peaks are evolving over the cycles, and we see that our positive thermal gradient has trending that looks very similar to the simulation of loss of active material at the positive electrode. This gave us the sense that this degradation mode was cathode-centric, where the other was anode-centric, which we had already diagnosed in our prior study. And so this really gave us the sense that by controlling the temperature in the battery, we can also control which electrodes are experiencing more degradation over time. And so we thought a lot about operating conditions. And so collaborating with Partha Mukherjee at Purdue University, we looked at how batteries behave in different operating conditions. And that means the C rate, or how fast we're charging. So you guys can use different chargers for your phone that charge either slow or fast. The same is true for electric vehicles. So on the left-hand side, we're going from slow charging to fast charging. And on the bottom axes, we're going from low temperature to high temperature. And what is plotted here is the temperature rise over a charge. So we would expect that if we're charging fast, we have more temperature rise, which you're seeing in the top left there. We also have more temperature rise at low temperature because there's more resistance in the electrolyte of the battery. Things are more sluggish due to that low temperature. So in the top left, the batteries are experiencing a large temperature swing over a natural charge. So they have less sensitivity to spatial thermal variation compared to those on the other pole, where we have low temperature change over the cycle. So we're moving ions slowly and at a moderate temperature, where they're operating in their most ideal condition. And what was interesting to us is that Professor Mukherjee's model could also model lithium plating probability. And again, we see that plating probability in the top left. And that's as we expect, because things are moving more sluggishly, and you would expect the accumulation of lithium ions. But what was interesting to us is the experiments that I've been showing you were actually at this complete opposite side of the plot, where we expect there to be no lithium plating, and we have now identified a highly plating propense condition. And so this was exciting to us to say, hey, we can have this high-risk case in an environment that we did not initially think that we could. And so what these findings have identified to us is that we can tailor aging of batteries based on their temperature environment. And this is important because companies that develop batteries want to tell you that their batteries will last for 10 years, for example. But to say that, they need to get those experiments completed. So they're looking for ways to accelerate the degradation behavior to tell us how our batteries will degrade. And we can also use this sort of understanding to develop better interactions between our battery cooling to prevent the cooling from producing undesirable conditions within the batteries. Okay, so what we observed here is that mild thermal variations on the orders of 1 degree can have a significant impact on the local electrochemistry and cause degradation. So from this point, we went to even look a little bit further into what's happening locally from these temperature environments. So now my colleague at Iowa State is looking at configurations where he can modulate those thermal gradients. So I showed you conditions where we had 1 to 2 degrees, and he's developed a unique setup where he can modulate between -6 and +6 degrees of temperature variation from the positive to negative electrode. And without doing any electrochemistry, the battery is simply resting. We observe the battery's voltage changing when it's subjected to these temperatures. So why is that? There's 2 things that could be impacting the cell's voltage when it is resting, and that is the electrodes that are held at a specific temperature, so their redox potential is impacted by temperature. And we all kind of remember those standard redox potential tables in our Gen Chem textbooks. They're very sensitive to temperature. The other thing that could happen is we have the evolution of a concentration gradient within the electrolyte. The ions are kind of drawn towards that warm side and sparse at the cold side, and that causes the observation of a potential difference on the cell. So what we did was look to parse out those electrode and electrolyte phenomenon to understand how these voltage changes are developing. And so first, looking at the electrodes, we collaborated with Laurent Poulin from UCLA. He does some really unique electrode entropy measurements. And here, this is based on the simple entropy equation. And what we do is we slowly charge the battery and then rest the battery and change its isothermal condition. And that results in a value of voltage change with respect to temperature, or the entropy term. And we did this with 3 different cell types. A full cell with the layered electrodes on both anode and cathode, and then half cells where we have a layered electrode and a lithium electrode. And so we were able to do this at various states of charge, but looking specifically at 50% state of charge, we can see the voltage difference between the anode and cathode. That's how we get energy from our battery. And then what we can do is look at these, let me point out that what you're looking at is these voltages of the anode and cathode at different isothermal temperatures. And although it's kind of hard to see on this scale, the anode has a larger slope than the cathode. This cathode is a more flat line there. But we can also use these measurements to simulate a thermal gradient. Subtract the voltage of a cathode at one temperature from the anode at a different temperature. And this allows us to isolate the electrode potentials from the electrolyte phenomenon. And so now we've created this plot on the right here, which is telling us the predicted thermal gradient response of a battery and its slope at different conditions, similar to what I showed you in the full cell, but this is simulated based on the electrode data. And notably, this phenomenon is state of charge dependent. So what I'm showing you on the right is a state of charge, so the battery is fully discharged. And in the fully discharged state, the battery is most sensitive to its electrodes being at different temperatures. So if I just incorporate the electrode component into what was observed by Todd Kingston's group, we only see about 0.2 millivolts per Kelvin shift from the electrodes. That leaves a lot. There was a 1.4 millivolts per Kelvin change as a result of temperature. So that leaves much of the component in question, which must now be related to the electrolyte. So what is interesting here is that a majority of this is coming from local solvation and concentration as a result of the electrolyte. So to study this, my postdoc at NRL, Lewis Morris, who's now transitioning to Argonne National Lab, developed this very simple H-cell test environment where we could hold one electrolyte and lithium electrode at a higher temperature than the other and measure the voltage difference. So what you're seeing on the right is Lewis changing the temperature of one of those electrolyte vats, and then we are tracking the voltage, and you can see that the trend of the cell voltage is very well agreeing with the temperature profile that we're applying to the electrolyte environment. And this very reliably produced a 1 millivolt per Kelvin difference in voltage across those electrolytes. So what we're seeing is that we have a contribution from electrodes as well as solvation. There's a little bit of that voltage shift that we are still not capturing by isolating electrodes and electrolyte. And this is likely coming from the interface, but it's something that we are still eager to investigate. But what was also interesting about this H-cell environment is that we could also probe different types of electrolytes. And we saw some really interesting trends. So we could do things like maintain the cation type, but change the solvent environment. In that first one there, 1 molar LiTFSI and G2. So we're using a glyme electrolyte now instead of a carbonate. And now we see that coefficient increases almost twice. So now in glyme environments, the electrolyte is much more sensitive to temperature than in carbonates, which is very interesting. Also, if we change from a lithium cation to a sodium cation, we now see that the sodium system is less susceptible to temperature than lithium. And that's likely due to the larger cation that is present in the sodium environment. But this also tells us that we can use these sort of components of the electrolyte to develop a battery that's less sensitive to changes in temperature, making it inherently safer from the very fundamental design. So in collaboration with Kelsey Hatzel at Princeton University, we wanted to look at solid electrolytes. So solid electrolytes are a very compelling topic of research because liquid electrolytes contain flammable and volatile solvents. So they're a key component in that thermal runaway event, where if we have a little bit of heat in the battery, the electrolyte really accelerates the battery going into this catastrophic fire event. And so solid electrolytes eliminate that component. And so her group designed an experiment to mimic our experiment in liquid systems, but in solid systems. And what we were really surprised to find is that the electrolyte still has a sensitivity to temperature, but it's an order of magnitude lower than that of the liquid environment. And the value is very close to the sensitivities that we observed on our active materials, our cathode and our anode, which are solid materials. So we think that these thermal coefficients are strongly correlated with their phase as well as their material properties. And again, this is an example of another reason that solid batteries are likely safer, because they have this resilience to temperature. Okay, so since electrolyte behaviors dominate thermal gradient responses in batteries, electrolyte selections can make cells more resilient to temperature variations. And so I kind of showed this already, but the electrolyte behavior makes up the majority of the thermodynamic electrochemical response to thermal gradients. So we were interested in applying this finding to intentionally plate lithium metal. So I showed you this little cartoon of a lithium-ion battery. So the layered structures are what give us those many, many cycles, and that's why the lithium-ion battery has revolutionized our portable electronics and electrification of transportation. But what a lot of researchers are interested in doing is collapsing those layered structures, because they take up a lot of volume and weight. And most prominently, we observe this at the anode. So the idea is that we accumulate these ions and then intentionally plate them as metallic lithium. So now our battery is 40% smaller and 50% lighter. The challenge of doing this is plating in an ideal morphology. I showed you those dendritic structures that everyone sort of blames on our battery failure modes and fires that we observe. So temperature is an interesting way to control the morphology of this lithium plating. But this is also a unique configuration where we can think about using temperature as a lever early in the design process, because we don't yet have the packaging of this type of battery. I mentioned the different thermal conductivities and components of lithium-ion batteries, but notably now when we replace the graphite with lithium, lithium is a metal which has a much higher thermal conductivity than graphite. So we have high thermal conductivity at one electrode and low thermal conductivity at another. We also have actuation of the battery, where the lithium will be plated and stripped on every cycle, which causes the battery to sort of oscillate upon cycling. So since the packaging is unknown, and we know that heat will accumulate at the cathode, we can think about how to use the battery's temperature to allow it to operate in a more ideal configuration in its future designs. So I'm kind of pointing out that the heat accumulates at the cathode, and I'll show that later on. And so I've been talking a lot about one particular condition in lithium-ion batteries where the thermal average is shifted to the warm state. And the actual magnitude of thermal gradient is about 2 degrees. Now I'm going to show you how we use sort of a low temperature condition with a small thermal gradient to make plating more desirable. Okay, so this is a video of intentionally plating lithium metal on copper at ambient conditions. So we can see observations of these sort of spiky, whiskery structures, especially towards the end of the cycle there. You can see sort of a beautiful dendrite popping up at the very end there. And we see these two distinct regions. There's one closest to the electrode that's, you can almost see a line there that's separating these two regions. And this is a shift from base growth to tip growth. So the plating is happening from the substrate up initially, and then the opposite happens. And that tip growth is where we often observe these dendritic features. And so we're doing this at a quite high C rate, something like charging your battery in 2 minutes instead of 1 hour. But you can see that these phenomena evolve. And so by changing the temperature environment, we still have these two distinct regions. We have that sort of base growth that shifts to tip growth because we're plating so fast. But by changing the temperature, we again change the morphology of that plating. And we can see we have these sort of compact columnar type plating, which is more desirable. And we can sort of envision that this sort of plating can happen more repeatably over many cycles without losing capacity. So this is really interesting. In this case, we're actually allowing the positive electrode or the lithium source to be hotter. So we're leveraging that observation that the cathode will be hotter in these types of configurations than in lithium-ion batteries. Okay, so this is just a quick example of how we can use temperature as a lever to smooth lithium plating and get higher energy density out of our batteries, and consider the temperature early in the design to facilitate these higher energy types of batteries. Okay, so I'll quickly summarize the findings. Temperature variations lead to performance and safety concerns in commercial cells. So this was a very strong motivation of the applied observation that battery safety is compromised by different thermal environments to help us understand the role of temperature locally to better design safe batteries. Mild temperature variations on the order of 1 degree have significant impacts on local electrochemistry that cause rapid degradation. So we have, 1 degree Celsius is a relatively small value. We know that we have temperature variations within large battery packs that are much larger than that. Electrolyte behaviors make up the majority of the thermodynamic electrochemical response to thermal gradients. So this gives us the understanding that we can carefully select electrolyte components to make batteries that are more resilient to thermal gradients and their thermal environment. And temperature can be used as a lever to smooth lithium plating to demonstrate higher energy systems. And considering, this is sort of a main point that I'd like to make, but considering temperature at the design phase can help lead to more efficient systems. So we're removing heat from batteries with cooling that also requires energy. So we're using batteries to store energy, and then we're using some of that energy to cool the battery. So that connection can be more efficient and produce longer lifetimes of batteries. So that's something that I'm very passionate about and excited about. So with that, I'd like to acknowledge the many people that I've collaborated over the years with to show you these findings. And I most recently transitioned to the University of Kansas. I have a couple of students that I'm working with, but I'm also actively recruiting. So I'd love to meet you and hear more about your ideas and how they relate to the future of batteries. And so thank you very much for your attention.
Please join me in welcoming back to the stage 2026 ACS President Rigoberto Hernandez.
Thank you. Thank you.
Good. So Dr. Carter has offered graciously to take questions from the floor. I'll ask those who wish to ask questions to please approach one of the mics, either on the right or the left. And we are fortunate already to have a couple at the mic. So we will start on the left side, please.
Thank you very much for the great talk. This is Ruel from Dow Chemical. So, let me see.
I can hear you.
Good. Thanks. So in thinking about both the thermal gradient effect study and also later on the electroplating study, I was trying to, think about how to transfer that knowledge into the real situation, because I somewhat deal with the automotive sector, so
okay.
that I have to think about electric vehicle batteries too. And with cylindrical batteries, it seems like it's common to cool things from the side. So that's normal to the anode cathode stack, like you were showing. And then with prismatic cells and maybe with pouch cell stacks too, you tend to cool it from the edges, so it's along the direction of the electrodes. But these are all packed in metal casings too. So I was starting to get puzzled, how come we're not seeing more catastrophic failures? Or are they cooling it from the right direction, or that the metals just redistribute the cooling enough that we don't get as much of a problem as we would expect?
Yes, great question. So I think, so I mentioned, we're applying 1 to 2 degrees of difference in a single layer. And we're still trying to understand what temperature difference manifests between layers in conventional operation. Maybe it's an order of magnitude lower than that, for example. But because it's still evolving, this is likely contributing to the capacity fade that we observe, which is typically somewhat linear. But the question is if we can kind of eliminate this component that maybe is a bit of an afterthought. So we apply cooling, after we design the cell. But if we are minimizing the thermal gradient, would we actually get better cycle life? Because I think there's always thermal gradients. It will always cause degradation based on what we've observed. We've yet to see within lithium-ion batteries a thermal gradient that improves performance, although we were hoping to find that. So I think in this case, the idea is to minimize it. And as you were mentioning, the geometry plays a role. So I think something I'm eager to study is the interaction between the geometry and aging. So cycle life with respect to the cooling geometries. I don't think this has yet been investigated much. There's also a pretty big difference in the management of heat based on the aspect ratio, as you mentioned. So there's like high thermal conductivity axially versus radially and things like that. So I hope this answers your question.
Thank you very much.
Yeah.
We'll take a question from the house left.
Thank you. Fantastic visuals on the talk, but my question was about electrolyte selection. You mentioned a surprising difference between glyme and carbonate bases, and to me I see ether or carbonyl, and I was thinking, is there something related to chelation of lithium, or do you have any comments on that hypothesis?
Yes. So my postdoc who was leading this is an electrolyte guy. So he taught me a lot about solvation environments. And so I think it is related to like contact ion pairs versus solvent separated ion pairs and things like this, where the temperature is actually changing or having a larger effect on the proximity between the solvent and the ion in the in the glyme environment compared to the carbonate, which is very interesting. And often when we compare electrolytes, it's more for the ion transport performance and also SEI development. But this is sort of an unexpected thing that we should look at. And we also observed that we could look at different ratios of carbonates and things. And the trends that we observed were a little bit incongruent with what we would think from just comparing things like viscosity and conductivity. So the solvation is playing a very important role.
So the next question from house left again.
Thank you for the talk, and as much as I enjoyed this speech, I regret that my chemistry professor wasn't here because he would definitely love this speech. So there was a sort of brief mention of solid-state electrolytes, and kind of an idea kind of popped in my head. I was wondering how applicable your research can be when it comes to, I guess, the development of like solid-state sort of batteries, because there's been, I guess, a lot of talk in like the electrical vehicle industry about that.
Yeah, that's a great question. I think the reason why I started collaborating with Professor Hatzel was this sort of question because there is more heat that evolves in solid state batteries, and often we heat them to even do typical cycling. So instead of operating at ambient conditions. We heat to like 60 C or something like that. So it again begs the question, if we're going to apply heating or use heating in the packaging, if we have a better understanding of temperature variation early on, we can use the temperature to improve the performance. What we were a little bit surprised to find was that they in general seem more resilient to temperature. So they don't mind as much having spatial variation in temperature, which is a good thing. So I think valuable to study, but maybe they're a little bit less sensitive to these phenomena.
Great. And one more question from House Right.
Yeah, thank you. So I was just wondering if you could go more in depth on the use of solid electrolytes. I was wondering, I guess, if the physical resistance to dendrite formation could be leveraged to kind of make a more resistant battery, or if, I guess I'm just imagining like a dendrite growing through a solid electrolyte would be a lot more challenging than a liquid, for example.
Yes, I think this was like an early expectation of solid-state batteries, although there's been a lot of observation of lithium growth through like grain boundaries or cracks. That interfaces are a massive challenge when you have solid, solid, solid. So the liquid always kind of fills the gaps, right? There is surprisingly more sort of lithium dendrite growth. It's not exactly a dendrite in this case, but it's like a similar phenomenon in solid batteries. But the mechanisms are completely different. So, yeah.
Towards the end, you started to indicate some measurements that felt like an inoperando the conditions, and I was wondering to what extent you might, in those conditions, what would you measure, and how might you use feedback in order to change the temperature settings and have optimization?
Yeah, great question. This is something that I'm starting to look at KU. So we're looking at doing even some simple COMSOL models or things like that to look at instead of maintaining the battery isothermally with its cooling, could we modulate the temperature based on what we know about how to make what temperature the battery would like to be? Yeah. So it's a big question, and also how would we practically apply modulating temperature to a battery is a challenge, but I think it's a grand challenge worth exploring. So we actually did some interesting experiments at APS at Argonne to look at the temperature inside a battery with different like fan speeds and things like this. There's a lot of data to go through, but I think it will be very interesting.
Super cool. Just one last question, just because some of us have electric vehicles and we don't understand why it is that it starts to prepare its battery just before we recharge. What's going on? Is it only thermal, or are there other things going on?
Great question. Yeah, so I talk a lot about this sort of idea of like smart cooling, but we can also do careful charging. So we could change the rate that we charge based on the state of charge. So like in some portions of the charge, it will accept the ions better than other portions of the charge. So it's looking for things like that. It does heat the battery, for example. And then also, sometimes if you use different chargers, so at home you're going to charge at a slower rate than at a fast charging station, but each of those conditions stresses the battery in different ways. So I think some cars will even tell you how many times you might want to fast charge versus you'd rather use the slow charger. So it has a lot of smart data that it's processing. It's processing data related to your last drive and the last charge and things like that.
Super exciting. The future is already now, and the future is going to be a lot better because of the work that Dr. Carter is doing. Let's thank her for a wonderful presentation.
Thank you.